Good morning. See if the technology works today. Share screen. All right, just to make a final note about the project. Using Desmos to guess and check. C is okay. And I want to, if some of you want to essentially try to take this to the next step, I guess I would almost say just like on your own as extra credit or something. I guess it would be, I'm just going to guess about this a little bit. So, you know, because not of calculus, but algebra, you know, for instance, that you know what that area there needs to be. And so you slide your C up and down, and remember, because of the kind of the neutral axis of this, maybe that's where the ellipse actually turns around. C is actually kind of that distance right there. Like you're sliding it down a certain amount of C so that, if you will, the leftover distance up there is correct, giving you the correct area in green. And if you take that area in square inches times 84, then that gives you the right amount of water for your weight. So all I really need from you as a group is, you know, what that weight is, what your paddler weight is, plus 44 pounds, and your calculation for what that error is. And so based on what that C is, does it make sense? It also kind of determines what your equation is, or what these points are. It determines where that hits. And, you know, if you think about what that would mean algebraically, let's see. So yesterday we said for sure it was because the X radius was 13. Maybe I'll write that as a number that's been multiplied out. And I don't know what 6.5 squared is, so I'm going to figure that out real quick. And then because we said Y has got to slide some C value, 6.5 squared is 42.25. So since you know that this point is, as we said yesterday, something 0, you know the Y coordinate is 0, you can actually write an equation for the coordinates of that point based on C. So again, what I'm talking about here is if you want to go above and beyond and think about this question, I don't know, I guess a little bit more deeply, or if you're not satisfied with guessing, or if you're just curious to see if you can get this right. I'd say it's cool if you can do this, number one, because I'd give you some points for it no matter how far you got into it, and I would help you get it all the way if you want to over the next, say, weeks or so. But then before we're done with this class, you actually will be able to do this. Like you'll be good enough, as I said yesterday, at integrals, that you'll be able to survive it even when it's this complicated. But of course, if Y is equal to 0 in this equation over here, then I can actually I can actually solve this for x. And that literally is the x coordinate of that point right there. And then the y coordinate would be the same thing, but negative. So does it make sense then that you're sitting here with this integral, and right now c is a variable. In other words, you're trying to solve for c, and you're just guessing and sort of cheating your way to an answer to that using Desmos. But you wouldn't have to. If you took this x right here that you just found, and you put it in here like that, or maybe even better, you, actually, I think I want to leave that. Maybe even better, you said, I'll just call that 0 and double it. Do you understand that because of symmetry? Maybe that'll make your life easier. And as my project said, I'm going to pull this up just so I don't screw it up. Go. Can't find it. I have stuff to do in my head. So if I solve that for y, I would have, let's see, 1 minus x squared over 169. And then I would multiply both sides by 42.25. And then I would square root both sides. And then I would subtract c, something like that. That's what y would be equal to. With respect to x, and you're treating this c like it's a constant, and you actually know, and this is the important part here, you know what this is all supposed to equal. That's what's so different about it. That area right there, you actually know the answer to this. So you're trying to take an integral, treating c like a constant, but you actually know what area that's supposed to be. Again, that's not what you're used to. You're used to c being some number that you do know, and then just asking what's the area. Well, this time you're trying to solve, well, actually a kind of a harder question. But again, I show you this because this is a genuine application. So, and this is beyond us. Do you understand that? Like, I mean, we're barely just learning what an integral is. And so to give you a problem this weird is kind of crazy. So again, I'm saying extra credit, like don't do this. But if you weren't allowed to cheat, if you didn't use some sort of cheating software on the calculator, maybe you just cheat and went into, well, I'm going to show you some of these. I'm not sure when. Maybe I'll show them to you now. There are places you can cheat online and ask what integrals are, and it will tell you. Maybe I should do that right now. But the point is you've got to kind of cheat to get this. And as I've been already hinting, integrals are hard, ultimately. Real integrals are hard, and this is a very big problem. So anyway, if you want to take that on for extra credit and sort of try to get past cheating, turn it in by Friday with the cheat answer and so forth, great, you're all done. And then if you just want to play with it beyond that and see if you can make any progress and, you know, arrive, if you will, algebraically or using calculus at the same C value you got by cheating, except, you know, more accurately and with more integrity because you did it under your own power. Awesome. Good for you. And as I said, I'll help you do that.
Yeah, there's a website called, it's literally just Integral Calculator, and it's pretty helpful because it'll guide you through some of the steps.
Yeah, and to that end, I think I am going to show you some of that stuff right now. So I'll show you some of the things I've found myself. And this one is just scandalous. Like it is, you could literally cheat your way through this entire class, especially in this format where, you know, you're at home and you could fake the teacher out because it's not just giving you the answer. I mean, obviously I'm giving you credit for your work. Like this actually shows you all the work on top of it. And I'm showing you this one because you live in a world where, I don't know, cheating in education is actually pretty easy to do. Almost to the point where people don't even see it as cheating anymore. They just see it as getting help from something. But I'm just arguing. I want you to know that this stuff is out there just so that you stop and think, you know, do I really want to do this? But also because it helps. Like if you really want to get an education, sometimes problems are hard and you need to reverse engineer. Like I don't know how to do it. And so I need to see somebody do it. And you know, my goal is not just to copy down what they said without thinking about it. So I might copy down what they said, but I'm going to stop and educate myself, like stare at it a bit and go, oh yeah, I see, that makes sense, and learn something from it. As I think I told you guys before, last year I taught Calc 4, which I'd never taught before. And I found that's what I did to learn it. Like I watched videos of people doing problems like I'm doing for you, or I tried to do a problem and I just wimped out and couldn't get it right. And so then I went to places like CY Math and I said, here, you know, answer this question for me. And then I watched how it was done, and then I learned, and like, and then I could teach the class. So I think this stuff is helpful if you use it correctly, I guess is what I'm saying. Let's see. Integrate.
I have found that calculators like this are especially helpful on like the homework when there's not the video link.
Right.
And
Yeah.
I don't have, if I'm not working with my tutorer, and like I only get meetings once a week, because you can get a similar problem and see, okay, did I start this the right way? If I couldn't find like a video online or there wasn't a link, it was really helpful to be able to see like, where is the mistake I'm making when I can't figure it out? And you can get a bunch of similar questions on the homework to look at and see, can I do this right? Do I know where I'm going wrong?
Yeah.
That's the thing. It's like when I use it too, like I don't use them for an answer. I use them when I can't navigate my way through it. And I'm like, well, how do I get through this? And then it's like, oh, okay, that makes perfect sense. And then I learn something, and I'm not just like copying an answer over, you know, like.
Yeah. Nice job. And I'm encouraging you to do that. To that end, I don't think it is cheating. It's how you're getting help with something that you don't understand. So, you know, as long as you use it to your benefit, then good for you. Well, let's see who has a good idea. I don't know how to type square root. I've got to type with a keyboard.
It's SQRT.
You are correct. Thank you. This particular one, thank you, Eve. CY Math is a little persnickety, like you. If you don't know how to type square root, then you can't find it and so forth. There's another one I'll show you in a second that's incredible. Like if you said integral here, it won't do it. Like you got to say integrate. But as it turns out, this question is similar to what you're doing in the sense that you have the square root of x squared minus something squared. And notice it's nice that up here it tells me this is what it thinks I typed. I see there's 2 dx's up there, so maybe I don't need that second one because it's put it in there for you. So that's cool. So hit enter. It says use trig substitution. It tells you what substitution to use. It says if x is 5 secant u. First of all, does that strike you as x is 5 secant u? Where did you get that? Well, that's coming in a later chapter. Trig substitution is really cool in certain situations, and that's why this problem I'm letting you cheat, because you're not good enough at substitution yet to survive this problem algebraically. And so if x was 5 secant u, then dx would be 5 secant tangent. Do you remember that the derivative of secant is secant tangent? You probably don't, but it's on your note sheet. And then it, you know, step 1, step 3, step 4, step 5, step 6, 7, 8, 9, 10. Wow, this is a hard problem all the way down to, good Lord, this is a huge problem. All the way down to 24. So you see what I mean? Like if you're sitting in a class and your goal is just to get your calculus credit, like you could just go type all of that in and the teacher would be like, man, nice job. Like you totally know this stuff. Oh, no, I don't. I just stole it offline. I don't know anything. Notice how crazy the answer is. It's got x squared over 25 times x. It's got logarithm in it. Wow, that's amazing that problem could be that complicated. And notice it doesn't look that different than what I put on your test. And yet somehow this one's crazy hard. So again, I show you this because this is a cool website if you're stuck, if you haven't seen it before. And also to illustrate how difficult the project that I gave you would be if I didn't let you cheat on Desmos to get the answer. And how difficult your job is going to be if you actually try to do what I just suggested for extra credit a minute ago. And how good you have to be at substitution to do that. So that's just interesting. The other one I've seen, I don't know why you need another one. That one's actually pretty good, but I guess I just want to show you this really quick because it's kind of cool. And I might have shown this to you, my Calc 1 students from last term. I might have already shown this to you, but Wolfram Alpha is another one. And it's kind of, I don't know if the word is idiot proof. I don't know what to call it, but basically it has the same thing. It's just some, line up here. Find the integral. Notice I spelled integral wrong. I'm just going to see if this will work. Of 6 sine of x squared. Notice it doesn't say I don't know what to do, like CY math will do. It says you're an idiot. Integral is spelled like this, and then it goes ahead and answers it anyway. This particular website does not give you the steps, and so if you're looking here to cheat, then you have the right answer, but you don't get any steps. You get the steps in CY math. If you pay some money to this site right up here, then you unlock the steps, and then you get all the steps. So this one isn't all that helpful, but the only reason I show it to you is, number one, there's a whole bunch of websites like this, and there's, for those of you future teachers, there's kind of an interesting argument as to how much do people need to actually know. And we're going to spend a whole term learning how to take the integral of everything, and I just showed you how to get the integral of everything. I mean, if you're getting paid to take an integral as a part of your engineering, like what would you do? Would you write it all out by hand, or would you just go in here and get the answer and get on with it? Pretty interesting question.
I think the part of the argument of that, though, is even though this tells you how to take the integral, it definitely does not tell you how to apply the integral. Yeah. Like, I don't know if you could type a word problem in this and be able to find, oh, this is how this is the steps I need to take to do that.
Yeah, very well said. And to that end, Eve, that's exactly why I spend more time trying to teach you guys how to think and how to understand what an integral is, because that's actually the hard part in the real world. And, all but the future math majors, if you will, that like this stuff for its theoretical reasons, the practical people just need Wolfram Alpha. And then, like Eve said, they have to be smart enough to understand, hey, this is a situation where an integral would help me. So, and coincidentally, I'm teaching statics right now, and we're using integrals all the time as a part of the calculations we're making. So it's a thing. Like and the people that just kind of, I don't know if the right word is, one, either cheated their way through calculus, or number two, were too mathy, like not thinking about, what an integral is, have a lot harder time with, the engineering classes that actually have calc as a prerequisite. So
I think also you have to know how to do things to build upon it. Yeah. So if you are using just calculators, there's going to be a point as you further in your education that calculators are not going to be helpful. And if you haven't built upon that, then you're probably going to have a really, really hard time.
Yeah. And I don't actually, I feel like I'm preaching to the choir here because you guys are this far into school, but I just like to reason with people, I mean, you're in school because you want to get a job. I mean, that's kind of the ultimately, really, if you break it down, that's what you're doing. I want to be able to get a good job or something that, and that might be something I enjoy. It might be something that pays well, ideally all the above. But one of the things I always kind of remind people is that's important. Absolutely. And that is what you're doing here. But you're also going to be whatever, you're going to do that for 30 years. And so do you want to just barely have made it there and be terrible at it and be the worst person there? Or do you want to be somebody that actually kicks some butt? Like you actually really know some things, and maybe you're the one person that can figure out that hard word problem situation just because you've trained yourself. Like there's no shortcut to that. What you do, banging your head against like these extra credit problems in these projects, which is why I give these projects, is what teaches you how to think, and what can potentially make you awesome at your job and not just survive. But that's very much a personal choice. And I also know, given that this is a community college, a lot of you have competing interests, like you have a family or a job and other things. And so although you would love to spend hours doing this, you can't. And that's for real, for sure. But all that to say, use these tools. These are awesome. These are incredible tools if you use them correctly. you know, obviously I'm asking you to commit to not use them on a test, but realistically, you should be using them everywhere else. I'm constantly telling you to cheat all the time. And I've showed you all this stuff long before I should have, if you will. So especially CY math, super helpful to kind of help you reason out, help you reverse engineer. I mean, if I stare at the steps this person took or this machine for all I know, and I, you know, follow it all the way through, I actually might be able to go, oh, I see how that works now. The one thing that's kind of cool about just a random problem I picked though is notice this, what did it have? 25 steps to it. Like, you got to be awesome at algebra. Like, you got to be careful. You can't do 25 steps of something if you're not really careful algebraically. And so that's kind of why the problem I did for the test yesterday at the start of class was about that. Like, be really careful with your substitutions. Make sure you're, you know, writing super clearly like this, using up a little too much paper and writing out all the steps, being careful. Notice this problem right here has turned into, well, ULAND. And notice I never said integrate it from 6 to 12 or something. It's an indefinite integral. And so right here in step 3, they have survived in getting this into a totally different letter. The question is just, can I do it now? Like, is this easier than it was before? It's really weird to think that the square root of x squared plus 25 turns into the integral of 25 tangent squared secant. But I don't know about you, but I look at that and think I still can't do that. Maybe that's why there's a whole bunch more steps, because maybe there's even yet another substitution. Notice there's they pulled the, I'm just going to ramble here for a second, but they pulled the 25 out front. Yeah, we talked about that. Pythagorean theorem, that's interesting. Pythagorean theorem, tangent squared. They replaced tangent squared with secant squared minus 1. And so now secant squared minus 1 replaces that tangent. Why would you do that? Well, now it's secant cubed minus secant u. Notice that's not a substitution like we're with a new letter, but they're using a trig identity to change the way this thing looks. And then because of that minus sign, now there's 2 separate problems here. Can I take the integral of secant? Can I take the integral of secant cubed? And I won't go on, but you're still a long way from done. Like, that's hard. And so one of the things I just want you to know before we take off even further into integral land is integrals are hard. Like, in the back of the book, in the back of your book, there's a table back there that says problems that look like this: x squared minus, and it won't say 25, it'll say, and it won't even say 5 squared, it'll say like a squared. And there'll be a table, because it might be that it takes a tremendous amount of knowledge and even creativity. Like, who would have thought I needed to switch out tangent squared with secant squared minus u? Who would have thought that? Who would have thought to substitute x for 5 secant of u? Who would have thought that? I mean, that's brilliance, right? That's impressive. Who thinks of that stuff? And so if somebody does survive it, then, you know, please write this down so that, you know, all of the rest of us don't have to discover it or reinvent the wheel, if you will, from scratch. If one person reinvents the wheel, how about you share that with the world? And so integral tables are a thing. I'm going to show you that quickly now too, and then we'll get after it today. I think I have this in here somewhere. I don't think I've posted this yet because it comes up as part of our, I'm not sure I even have it here. Come on, integral table. I'll have to show it to you later. But I have an integral table that I found online that has 50 of them, 100 of them. And they're just lists. Like, what do you do if it's of the form, the square root of x squared plus a squared? What do you do? And it'll just kind of tell you what the answer is. And that is very much because integrals are genuinely hard. And so you want to play around with them. You want to learn how to reason. You want to, you know, get reasonable at being able to take an integral. But it's actually far more important to understand what an integral is than it is to survive the taking of some random irrelevant equation. That's kind of what I'm getting at. So
I don't remember where in the book, but there was a spot in the textbook that also showed a ton of like integrals and different formats. I don't remember exactly where it was in the textbook, but I know that it is in there. I remember seeing it.
Yeah, and it's usually, I think in your book, it's at the back. Pull this off the shelf really quick. Yeah, you're not going to be able to see this from where you're sitting, but I'll just hold it up anyway. Let's see, it goes down to 108. There's 108 different forms of integrals, and I'm looking at one. Let's see, we just did x squared minus 25, and there's a whole section of that. 68 through 75 are all integrals of that form. And I'm looking right now at number 68, which is the answer to the one we just stole off of CY Math. And so the end result of this class is very much learning how to use those tables, because there's just so many of them and they're so hard. If you wanted to get them all yourself, it would take 2 years to study integrals. You don't want to be that good. You don't need to be that good. That's kind of the point. So yeah, one of our assignments that'll actually be part of it is you just learning how to read that table and stealing some stuff off there. But we live in a world that's beyond that. Like even looking up at a table is kind of ridiculous. I just showed you CY Math, which has got them all plus more, all of them are there. And because that is, a machine, I would be willing to bet it can't do them all. Like if you just type something crazy in there, it'll probably say, I don't know, at some point. So here's one of the huge, and I've already hinted at this as we start chapter 6. I've already hinted at this when I introduced what an integral is. And I want to show you something amazing right now. If you've taken physics, you're going to just love this. This is amazing. And you also have some problems about this. So you guys know what, maybe from some class, certainly from physics if you took it, but what's gravity? What's the number that's assigned to gravity?
9.8.
Yeah. 9.8, and that's the metric version of that, meters per second squared. Does anybody know what the English or the standard version of that number is, not the metric version?
Would it be in feet per second?
Yeah, except feet per second per second.
Oh, okay.
It's 32, and I'll write it different this time. Instead of feet per second squared or meters per second squared doesn't make any sense. But if you say feet per second, that actually makes sense. And what this means is if you're on Earth, because of the law of attraction, Earth has got a lot of mass. And so if you get away from it, it's going to try to pull you toward it. And so in space, Newton's laws of motion, any two objects, any two planets are going to be attracted to each other gravitationally. And so because of the size of Earth, it's 32 feet per second. That means if I drop a rock, 1 second later, it's going to be going 32 feet per second, but it's speeding up at 32 feet per second, which means after 2 seconds, it's going to be going 64. And after 3 seconds, it's going to be going 96. That's what Earth does. What happens if you drop a rock on the moon?
It falls slower.
Yeah.
Because it's less massive.
Yep. Doesn't have as much mass, so it doesn't pull as hard. And so the gravitational constant pull of the Earth, I have no idea what it is. I haven't lived there very much. Maybe it's 10 or 4 or something like that. So it's going to fall a lot slower because it's not pulling so hard on it. So that's considered to be the acceleration of gravity, the acceleration of something due to gravity. So if I shoot an arrow up in the air, basically it's going to come back to Earth. It's going to get slowed down by the pull of the Earth. It's going to stop in midair way the heck up there, and then it's going to start speeding up and then smack on the ground again.
It's also what's holding you on the ground.
Say that again, Justin.
It's also what's holding you on the ground. That gravitational acceleration is constantly happening even when you're at rest.
Yeah, I had this amazing dream once when I was way younger in my life that gravity was in effect and not in effect. It was random. Sometimes it was in effect and sometimes it wasn't. It was an awesome dream. It was terrifying because you're just out there walking around and suddenly there's a car floating over the top of your head, and now you got to look out over your head so you don't get smashed by the car. And obviously the people in the car who were driving were thinking they were going to the store. Nope, you're 100 feet in the air now, and as soon as gravity comes into effect, you're going to fall.
That's super interesting. I've had dreams where I could control and fly, but I've never had dreams like that. That's neat.
I've only had one. So it's sort of a stupid addition, but physicists will say that's Earth's gravity. Stupid because we're mostly going to spend all our time here. So this is an acceleration. You're accelerating. Accelerate. I should know how to spell that, and all of a sudden I'm fumbling. Accelerate. All right. That's an acceleration. And based on calculus, and this is one of the coolest parts of the fundamental theorem of calculus, you can actually create the physics formulas. So watch this in action. So what this means is if I drew a graph and this is time, and since I was using seconds up there, I'll use seconds here. And if this is acceleration in meters per second, then it's always 9.8. Does that make sense? It's constant. It's always 9.8. But what would the area under that curve represent? And you sort of should know the answer to this. But if I went to find the area under that curve, and notice I don't need calculus to do that because the area under that is a rectangle. What would the meaning of that be? And I would like you all to know the answer to this. I'm guessing half of you know it right now.
The distance of that line.
It'd be velocity.
I've heard some good answers. Heard
Total
some good
velocity.
answers. Look at the units. What are you doing to find area? You're adding rectangles. What are the dimensions of that rectangle?
Meters per second squared per second.
So that's seconds, right? Your dx, or dt in this case, is seconds. And you're multiplying that by meter
Oh,
per
you-
second squared, right?
you just end up with meters per second, so it's the speed.
Seconds times meters per second squared. One of these seconds cancels with one of those seconds. You end up with meters per second. And as I heard one of you say, maybe you took physics. I wasn't looking to see who said it, but you get meters per second. Like, this is what's cool about an integral. So you're literally moving, because of integrals, you're moving from acceleration to velocity. So isn't that cool? Like, now, isn't that a natural curiosity? Like, if I jump out of an airplane as a skydiver, isn't it interesting just to think, how fast am I going right now? Well, I just gave you a, sort of a sneak peek. If we round this off to 10, then when you jumped out of the airplane, you'd be going 10 meters a second. And 1 second later, you'd be going 10 meters a second. 2 seconds later, you'd be going 20. 3 seconds later, you'd be going 30 because it's constantly increasing at 10. Does that make sense? Now, some of you sharper types might notice that depends on your, if your parachute's open, because friction is a big part of this. And this equation is sort of only true in a frictionless environment. So it's a little bit theoretical.
You have terminal velocity.
Yeah, and you got terminal velocity, which has to do with friction. Well, let's see. Yeah, let's go dt. We don't need to use x's. You should be able to take the integral of that. You get 9.8 t. And what's very important that's missing that is actually going to be really important for the first time today? So we have our first equation that acceleration is equal to 9.8 meters per second squared. That's an equation. And it's kind of cool that it has no variable. In other words, it doesn't matter what time it is, that's the acceleration. That's why there's no t in it. And you could say it's negative. Does that make sense? I could choose to say it's negative because that's always pulling me down. I probably should.
Yeah, it
Well,
always.
Just say duh, it's negative, but I think I'll put it in there. So what did I just find right there? Like, what is that?
That's the integral.
Yeah, that's the integral we just took, which is, we just figured out, velocity. The area under the curve has a physical meaning here, and it's velocity. That's kind of our.
Oh, that makes sense. So like the further you get out in time, the faster you're going, but the acceleration is staying at a level rate.
Yeah. Now think about the area under that curve. Does it make sense? You don't you don't actually need, you don't need to use calculus to find that area. In other words, if I said, hey, this distance right here is 9.8, and I said we went out to a time of 4, then wouldn't you say, well, then that's easy. It's 4 times 9.8. That's the area, right? Time times 9.8. Well, isn't that what the integral produced there? So in a sense, I didn't need an integral to find this, but the point is the area under the curve is telling you something real here. It's not just let's go find it because some math nerd said let's go find it. This is a huge part of why we know so much about projectile motion and how to fly airplanes and all these things, because we kind of understand how to control this. What does that C? This is really cool and really important. What does that C represent this time? I didn't just throw it in there just because I was going to get in trouble.
How high you are.
Yeah, what? Think about it. I'm going to give people some more think time on that before I just say yes or no to that.
Well, yeah, I mean, it technically would be because I mean, it's in the displacement spot of like when you put something there, it would move your graph up or down, right?
Well, think units for a second. Like we said, velocity is meters per second. What's the unit for that? 9.8 times t. What's the unit for that?
Meters per second squared.
The 9.8 is meters per second squared, but it's being multiplied by a time, which is in seconds, right? So this cancels with this.
Since the C shows up after the integral is taken, I think it's the starting velocity.
So I've heard height, I've heard starting velocity. Does it make sense, these terms, I mean, if they're going to add up to meters per second, they have to be meters per second. And 9.8 times t is meters per second. Does it make sense also that C can't just be 6? I mean, it's also meters per second as well.
Is that because you have to add them together?
Yeah. Now, if you took a rock and you dropped it, then because of 9.8, you kind of know how fast it's going as it cruises down. Every second, you know what its speed is. But what if I didn't drop it? What if I threw it down? Didn't it start with a faster speed? So
Yeah.
notice V of 0, like time equals 0, would be negative 9.8 times 0, which is of course 0 plus C. Does it make sense? V0, sometimes written like that in physics. That
So-
C is not just a constant, it's actually your initial velocity. So gravity pulls on something, whether it's moving or not, whether you throw it or drop it, it's always pulling at 9.8. Doesn't make any difference what it is. But you can start it off with a speed, can't you? Like an arrow, if I pull back and I shoot it, it is being pulled down at 9.8, but I gave it an initial velocity that's positive in the other direction. Or if I bump on top of the cliff and I don't just drop the rock, but I throw it downward, I gave it an initial velocity, and then gravity pulls on it from there. Does that make sense? So that C isn't just, oh, don't forget the C or it's -1 on your test. Like that C, because we're talking about velocity here, and it's the velocity when time is 0, that C is the initial velocity. And so sometimes you'll see this equation written as velocity equals negative 9.8 t plus V0, not just C as though it's just some random number that you throw in there that means nothing, but it's initial velocity. I'm preparing you for physics here by giving you that little V naught, that little tiny 0 down there. The 0 is kind of code in physics for initial. So if you see T0, it means initial time. If you see M0, it means initial mass, that kind of a thing. You probably won't see that in your textbook, but just understand this constant has some meaning here. So we literally just built this second equation. If you've taken physics, you're like, whoa, I've seen that equation before. So we have that one, this one, and now finally, let's take the integral one more time. But again, I want to ask you, why would I do that? Again, you sort of already know the answer to this, but let's do that. Let's do this again. What if this is time and what if this is velocity? Meters per second. This is seconds. And just to make a decent drawing, notice that has a slope of negative 9.8 and it's a line because it's t. And so I'm just going to kind of draw my graph looking like this. Just as we did a second ago, why would you want to take the integral of this statement? What is the meaning? What is the meaning of that? Why would I want to take the integral of velocity?
Wouldn't you get distance from that?
Exactly right. Notice you actually don't have to know, you don't have to know that. Like you don't have to look it up in a book. You can say, well, aren't I taking the dx, which is time, multiplied by the y value, which in this case is meters per second. Don't those cancel? And so we get meters. Ooh, that's distance. The integral of velocity is distance. Isn't that kind of cool too?
Yes.
If I drop a rock, so to speak, and I'm just curious, you know, one of the things you can calculate thanks to this formula, for instance, is if you're on a cliff and you're wondering how tall is this cliff, you can actually drop a rock, time how long it takes to hit the ground, and based on that time, you can actually figure out the height. Again, it's a little wonky because of friction of air and so forth. So you got to be careful to drop a nice smooth rock as opposed to a leaf, you know, which is going to take forever to get to the ground.
Also, if the wind is blowing, that could affect it too.
Mm-hmm. So go to it, my friends. If I give you the equation negative 9.8 t plus v0, and I say, go take that integral. Remember, v0 is a constant. We just don't know what it is yet, but you treat it like a constant. Can you take the integral of that statement? It's just a power rule problem. This isn't hard.
Yeah, wouldn't it just be VT?
Exactly right. That's a constant, so it's just going to be VT. But write out, scratch paper, what you think the answer is. So you should have added 1 to this t, to its exponent to be squared, and then divided by that 2, or multiplied by a half. The v0 has no t and it grows 1, and then there's another c added on to the end of this. We won't take the time to do it this time, but if you stare at all those units, what are all, actually I am going to take the time to do it. What are the units? Well, is it the 9.8 meters per second squared? And isn't the time seconds? So you have 2 of them, seconds and seconds. Hey, look, the units are meters. Well, of course they are. This is a distance. What about velocity times time? Isn't velocity meters per second? And isn't time seconds? Hey, they cancel. Look, meters. What's the unit for that c then?
Just meters.
It's got to be meters. Notice, like last time, if I said, what is the distance at time 0? I end up with 0 because there's a 0 for t, another 0 because there's a 0 for t, and all I have left over is that c again. So what does that constant mean in this context?
That means a different starting position.
Yeah.
Right.
That's kind of like the initial distance, or the initial position is what the way they say it in sort of physics. That's its initial location. So again, does that make a sense? Like if I'm on a cliff, does it matter if I'm on a 10-foot cliff or a 20-foot cliff or a 40-foot cliff? Yeah, it matters where you drop it from. And so this is how you get that involved. So our third and final equation is d equals, I'm going to write it this way, -1/2 times 9.8 t squared plus v0 times t plus d0. I'm using d for distance. Sometimes you'll see x in books because it was an x-axis or something like that. If you've taken physics, then you should be thinking, oh my God, I was using those equations and I had no idea they're related to each other. Like, this is where they came from. Thank you, calculus, is what it comes down to. So you can take physics and never know calculus exists, but does it make sense you're indebted to calculus, especially for this last one? You're indebted to calculus for the creation of this algebra formula. And now that you have the algebra formula, you don't need calculus anymore. You've got these algebra formulas. But what this means is you can kind of own everything about something's motion. There's sort of three things that matter when you're driving down the road. Where am I? I'm in Ashland right now. How fast am I going? And crap, I'm late. I better accelerate, right? That's the three things you're doing. Where am I? How fast am I going? And should I be going faster or slower? Oh, there's a cop. I should be going slower. So now you have all the equations that control those. So some of your questions today are getting at this beautiful calculus-induced relationship. And notice it works the other way. Remember, we took the integral. As we moved down this, we integrated to go to here, and we integrated to go to here. Does it make sense that we could use the fundamental theorem of calculus and take the derivative of that distance equation and turn it into speed? That's kind of what we did all last term. What you sometimes see in a physics book is exactly this, except for, again, interestingly, they'll replace this with the letter G because of gravity. And they'll say that because, well, is the problem metric? Notice this formula only works if the problem is metric. Whereas that number could be -9.8, but it could also be equal to -32 if this problem was involving feet. Does that make sense? Feet in seconds. And so it isn't just always 9.8. So you can't really put the number 9.8 in that formula. So 1/2 gt squared plus v naught t plus d naught is sometimes kind of how that works in physics. And again, I'm using that in a ton of classes after this that I'm teaching in engineering.
That also depends on if you're using SI units.
Yeah, so the units make a difference.
That is interesting that the units work out with each individual term of the problem. I've always waited till like the very end of the problem to make sure the units work, but
yeah, and sometimes you can actually let the units lead you to what to do if it gets really confusing. But it is important, as I just pointed out, to notice, hey, if this whole thing is equal to distance, then all of the three terms that are created in it must be distances. So it is a good idea, and most physics teachers will not put up with, you know, the laziness of leaving units off and so forth, because it causes students so many problems. So you got to attend to it, that's for sure.
Yeah, there's definitely problems where it's like you have to convert and, you know, put in like, you know, like 3 different things to convert a value to a certain thing that it's supposed to be.
Yeah.
Like for time and distance and certain things like that, you know.
Now notice, just so that you're kind of prepared for your assignment, notice that this is just stuff falling. Like it's gravity that's controlling everything. Does that make sense? But it's like if you're in a car, you're pushing the accelerator, like you have control over that. Your acceleration is not 9.8. It's whatever you want it to be because you're pushing the gas. So let me give you an example. Just some random examples. Let's see. If I told you that tree growth, I just made these up because they're kind of cool. Tree growth, and we'll measure that in feet per month. That kind of makes sense, right? Probably even feet per year. Trees don't grow that fast. Feet per year might even be a better example. And so if I said growth as a function of months is equal to -0.1, I'm just looking at my notes over here to see what I wrote down. Cosine of pi times m over 6 plus 0.2. Which one of these equations did I just give you? Did I give you the acceleration, the velocity, or the distance equation? You can answer that by staring at
Wouldn't it be velocity?
this. Yeah. I gave you the rate of change or the velocity. So that's where I gave you. And so what you should think is, hey, if the problem goes on and asks me about acceleration, then I'll take a derivative. If the problem asks me about position, then I'll take an integral. But you know, trees don't operate according to gravity. And so why do you think that this, why do you think I made up a cosine graph for this? Why would a tree's growth increase and then decrease and then increase and then decrease and increase and then decrease?
Because of seasonal growth patterns.
Exactly. So I made this up. I didn't go look this up someplace. But yeah, that's why there are rings on a tree. The whitish layers are the spring growth when there's lots of sunshine and lots of rain. The dark ones are the winter growth where they sort of don't have those ingredients, and so it grows really slow. So that's the only reason you can even count the rings at all. So they grow fast, they grow slow, they grow fast, they grow slow. Does it make sense that, well, I'll just leave it at that. So what if I ask the question, find out, let's see.
That's why modern wood is garbage, because of global warming.
I guess I'll say find feet at month, I don't know, 22, something like that. Does that make sense? This is kind of a cool problem. So what this amounts to is, in the real world, you only have access to its growth rate. But, you know, of course, for a person to say, that's great, it's cool that I know the growth rate goes up and down. But what I'd really like to know is, you know, when is the tree going to be 50 feet tall or something like that? Does that make sense? That's what I'd really like to know. Or, you know, how tall is it going to be? Well, 22 months from now. That's what I'd really like to know. But the problem is the equation doesn't tell you anything about, I can't plug M into this. All I'm going to get is the growth rate. I'm not going to get the actual answer. So does it make sense I need to take an integral of this? Do you see the logic in that? So it's just important you understand that an integral took us from velocity to distance. And, you know, this is a little broader of a question. It's not just the distance. It took us from a rate to the thing itself. So per the last test, I'm going to be a little bit careful. So I'm saying if I took the integral of, let's see, hey, I can pull that negative 0.1 out front since it doesn't matter and I'm confused. So I'm afraid I'm going to screw it up. I'll just get that out of there. And I'm thinking of it like this. Can I take the integral? What would the d out here be? It'd be d what? dq, dz, d what?
DT.
D, look at my
DM.
notes. This is a month foot graph.
DM DT.
Yeah, it's DM. It's like how many months. So if I take months times, well, as far as the velocity goes, this would be feet per month times month. And so if I find the area under that curve, the months are going to cancel and I'm just going to have feet. In other words, this is going to produce feet as a unit. Does that make sense? So my rectangles are DM and the height is feet per month. So months times feet per month cancels to feet. So that's why I'm taking an integral. That's this. I'm just helping you understand the logic and how powerful calculus really is. It is not about finding the integral of some dumb equation. It's about working your way from rates to amounts. So, okay, I'm a little worried I'm going to screw up that junk. So I'm going to let u be equal to pi over 6 times m. That means du equals pi over 6 dm. And because of this plus sign, I'm actually just gonna worry about this right now. And this screwed some of you up on the test. So now this is cosine of u. And then I also have to replace the dm with, well, du divided by pi over 6, or du times 6 over pi. So 6 over pi could be sitting out front. So all I really have is just what's the cosine of u du. Okay, that's easy. That's the sine of u because the derivative of sine is cosine. And the 6 over pi just comes along for the ride. So if I go back up to what I had a second ago, I sort of survived this all by itself. And notice the 0.1 is not, the 0.1 is not multiplied by the 0.2. So maybe I should even be a little more careful here and kind of say that. It's like I'm treating it as two separate problems because of that plus sign. So that means I have negative 0.1 times 6 over pi times the sine of u, but we said u was pi over 6m. So there, that integral has taken. I have not screwed up, at least I don't think, that integral right there. I've taken it correctly. And if I want to be sure, I could take the derivative of sine of pi over 6 times m and make sure I get back to where I started from. What's the integral of 2? Well, that's easy, 0.2m.
Isn't it negative sign? Oh, wait, I see your negative. Never mind.
It's negative because there was a negative out here, not because the integral of cosine is negative sine. Are you distinguishing between those two?
Yeah, well, isn't the derivative of cosine negative sign?
Yes. But the
So
derivative of sine is cosine, therefore the integral of cosine is sine. So no, it's not negative sine. It's negative, but it's because there was a negative in the problem.
Okay.
So do you understand that this is height? This is the height in this case, or the distance. And I do have to evaluate it because this said at month 22. And that's a little confusing because it's like month 22. What does that mean? From now, I guess I mean, maybe I should write it up here. I'll say from 0 to 22. So then I could evaluate this at 22 and at 0. And I would actually, all I knew was an equation about the rate of growth. And yet I was actually able to produce how tall the thing was. Do you see what I'm saying? You see how it's the same idea? I'm moving most of your problems in your assignment today. Your 6.1 assignment are going to be moving from a rate to, I don't know, I guess I'll use the word distance, but amount, I don't know what word to use, rate to an amount. Fortunately, because this isn't a physics class and we're not great at this yet, that's almost everything. That's what you're going to be doing. You're not going to be moving from an acceleration, although you might have a question or two like that. But for the most part, you're just moving from a rate to a distance, which involves taking an integral. So this problem I just gave you is a very good problem in terms of you understanding how to do your assignment today. Let's do another cool one. So let's say you have a job. And you can fill 30 orders per hour. Do you see how rate is such a fundamental thing in our culture? Like how it shows up all the time. It is not just speed of a car. Like you go to work and they're saying, okay, I want you to pack all these orders up that come in. And so you start packing them up and it's like, hey, I'm doing 30 orders in 1 hour. And then you might start thinking, am I good at this? Am I bad? Or more likely your boss might tell you whether you're good or bad at it. Like, hey, this person over here is doing 60 an hour and you're terrible. Like you gotta go a little bit faster. But you see how like that's a rate. So from now on, as I said, this class should ruin your life. When you see rates, you should think, oh, that's a rate. Cool. Miles per hour, orders per hour. That's
Jerry's per chair.
Exactly. Skiers per chair. Now, let's complicate this a little just for the fun of it. If you were sort of really fast and I told you that this was at the start of your shift, do you think that that rate would actually stay constant?
No.
It might actually go down as time goes on. Like it depends what order you're producing. Like I paid my way through college working in a mill, and you get tired. Like you're actually lifting lumber the whole time, and so you get your butt kicked. And so that rate was not a constant. So let's just say you're dropping at 4%, which is actually pretty good, isn't it? Like if you can only drop 4%, that's actually pretty good. Would you from algebra still be able to write an equation for this? And I guess I'll add this note here as a hint to you from your algebra knowledge. If I said, and by the way, you're going to be given the equations in your assignment. I'm just trying to teach you how to think a little differently so that you could actually do something in a job and, impress someone. Like that 4% does not just apply and at each hour, it's constantly going down 4%. Does it make sense after 10 minutes? You're not doing 30 orders an hour, and maybe only you're doing 29.6 orders an hour. You're slowing continuously. When you see the word continuously from algebra, that should ring a bell to you. That involves E. One of the classic equations you learned in algebra that models things. So we'll say P as a function of T, production and time. And so this orders is P and the hours is our time. So it's not seconds this time. That would be 30 times E to the negative 0.04 T. Perhaps you remember that. Notice I said start of shift. That's kind of code for time 0. If you put time 0 in here, don't you get E to the 0, which is 1? And sure enough, your production is 30. So that 30 is your initial production. So in your assignment, you'll just be given stuff like this. They'll say your production for the shift is 30 orders per hour, but or no, they won't even say that. They'll just say your production for the shift is 30 times E to the negative 0.04 T. And you might not even stop to think like what that means. But I would like you to actually be able to create that for yourself because you could actually make some money knowing this kind of a thing. So now you actually have a model for this. That's kind of cool. And so now you can answer questions that we won't ask, which would be something like, I wonder what, like an algebra question to ask would be, I wonder what your production will be at hour 7. Does it make sense that's not a calculus problem? Because all you have to do is put 7 in there and see what you're down to. Does that make sense? So, maybe that goes down to 22 or something like that. And so, then if you're the worker, if you're the boss or you're the person that's trying to improve the company, then maybe you could not just look at how many orders people produce, but also, who has longevity, and is there anything you can do to help people with that? Give them more breaks or set targets that are, fair so they can actually live with it, but also, challenge them a little bit. So what's calculus going to do to this question though? What are we going to do to it from what I just showed you today?
Find the integral.
Yeah, and what's that going to tell us? If this is production, if this is P production, which is orders per hour, and this is T for time, which is hours, what's the area under that curve going to tell us?
How many orders were produced?
Yeah. Isn't that an interesting question too? I mean, doesn't that seem super complicated to figure out? If somebody comes on at 30 orders an hour, but they're like slowing down all day long, like wouldn't it be cool if you could actually predict how many orders they did for an 8-hour shift? See if you can figure that out. I'm going to give you a second to think about it. So, question: number of orders in an 8-hour shift. All you knew was their rate, and yet, thanks to calculus, you could actually see how many orders they produce. That's a darn interesting question. I'm not just interested in rate. I'm also interested in what did you actually get done today? That's the basis on which you get raises or get asked to speed up. If you're taking an integral because I said take an integral, that's great. But I'm sort of very interested that you can picture this. Remember, you can still cheat. Make sure you understand that, yeah, it's logical. If I take orders per hour times hours, I'm going to get orders. And the graph of this is an exponential graph, and it's got a negative rate. So it's going to be dropping like I drew in this question right here. And so what we're really looking for then is that green area. I mean, that green area is literally telling you how many orders you did. That's amazing. That's just so cool. Make sure you started with the right thing. I just wrote the problem down.
Yeah, you got to start with substitution.
Yeah. Now, there's times when you can kind of say, well, I know the derivative of e to the junk is e to the junk. But then if I was doing a derivative, it would be e to the junk times the derivative of the junk. So if I'm taking an integral, it'd be e to the junk divided by the derivative of the junk. And that's true. That's like a cool shortcut. But we're not that good at substitution yet. So let's go slower. Like, just be careful. Like, let algebra, let math do its work. Like, don't try to do this in your head. So did you start by letting u be equal to negative 0.04t so that the problem became just e to the u? And that 30 can come out front. Like, I know how to take the derivative of e to the u, or the integral of e to the u. It's e to the u. That gets rid of that 0.04. But we're not done, because we also got to get rid of dt. So du would be equal to negative 0.04. The derivative of t is the derivative of t. Oh, okay. So if I want to replace that dt, then I've got to have du over negative 0.04. There we go. And I don't care about the negative 0.04 because it's just a constant. So I could pull it out front if I wanted to. And I could even divide that. It's probably a whole number. What's 30 divided by 0.4? 75, 0.04, so 750. 750, so this is actually negative 750 times e to the u. du. Now again, you have a choice here. Should you just take the integral of that and then put the t back so that you can use 8 to 0? Or are you going to do a third step up here and actually switch out the 8s and the u's? Doesn't make any difference. For some reason this time I want to stay in u land, so I'm going to switch them out. So let's see, what would that be? U is equal to negative 0.04 times t. I think that's 3.2, isn't it? Why am I not trusting myself? It's 0.32, isn't it? Yeah, 0.32. Good thing I didn't trust myself. And if I stick 0 in, of course, that's very helpful because it's actually 0. So there, now I can just stay in u's. I don't even have to go back to t's if I don't want to. Notice the integral sign is still there. Now I've taken the integral of e to the u and it's e to the u, and now it's not there anymore. So I just have to evaluate that at negative 0.32 and also at 0. And I'm a little bothered by the negative signs, aren't you? Because I'm thinking I'm not going to have negative production, right? Hopefully I don't have negative production. So e to the negative 0.32.
No, it ends up being a negative minus another negative, which is bigger than the original negative.
Good job. What I'm encouraging you to do is, like, are you always thinking? Are you just pushing stuff in, or are you thinking? Do you stop? Do you notice that negative and go, that's not good? Do you think like that? Like, slow down, reason, make sure stuff makes sense.
Yeah, I ended up with a negative number because I forgot to actually do the 0 part, and I was kind of like thinking I did it wrong because it didn't make sense. But yeah, that makes sense because I had to evaluate it as 0 as well and subtract.
Yeah. So when I put negative 0.32 in, e to the negative 0.32 is 0.726 positive, e to the 0 is 1. So then I subtract those. Oh, I get a negative number. So you end up with a negative number. So if I take that minus 1, I actually get negative 0.2738, and I multiply by negative 750, and I get, oh, positive 205. Isn't that amazing? All you knew was the rate of growth. You knew, and I'll just ask this rhetorically, but would you actually be able to collect data on a worker or on yourself and determine the 30? That'd be easy, right? I worked for an hour and I saw how many I produced. Hey, 30. But how would you get the 4%? You know, like, again, I won't answer that, but could you get the 4% yourself? Does it have to be given like a book problem, or would you know how to go get it? Obviously, if 1 hour later, if it wasn't 30 anymore, that would be kind of a hint, but we'll just leave it at that. And so you found this equation, but isn't this cool that even though this is changing continuously, it really is going not from 30 to 29 to 28, it's going from 30 to 29.997 to 29.824. It's actually continuously dropping. And yet you're able to kind of predict that, you know, maybe you say to someone, yeah, 4%, for someone to drop 4%, that's kind of normal. This is a hard job. So, you know, at the end of the day, is like if you produce 205, given that I understand people get tired, remember the answer should have been 30 times 8, which is 240, right? If you didn't tire out, that'd be the answer, wouldn't it? So notice, hey, 205 makes sense, doesn't it? Because it'd be less. I mean, do you do stuff like that? Do you think? I mean, I think there's 6 questions in your assignment tonight so that you have time to think. Can you go back to your graphing calculator and just cheat and steal that red integral right off of it? Can you go to Wolfram Alpha or CY Math, Desmos, and steal that answer just to kind of check and make sure?
It's amazing that Euler was able to come up with that continual natural growth number.
Yeah, this is such a powerful one because so many things in life change continuously that this model is just really algebraically cool. And to take all the math you've taken and not be able to build equations like this for yourself, I think is kind of a bummer. So it's one of the reasons I'm kind of bringing it back up. As I said, your assignment's just going to give you the equation and say, here's the equation, and you just go from there. This is powerful. I mean, you seeing this? Like, this is why calculus is in one sense nowhere. You go ask everybody you know, when did you use calculus last? The answer will be never. So it's simultaneously nowhere and everywhere. It's kind of a strange thing. But I don't know. I mean, the reason that you're sitting in this class, ultimately, this is the reason, in my opinion. Like somebody says, okay, you got to go take calculus. Well, if you understood it this well, you probably could see that if you were the boss of some kind of a production related company, you could actually use this. Now, would the company cease to run if you didn't? Could you make some kind of analysis, you know, not knowing this much algebra and, you know, just collect data on people and still get the job done? Yeah, probably could, but isn't this a cool tool? You know, the question is, can you speak this language? Can you speak this well enough to put it places? This is just a quick side note, and then I'll shut up and give you time to ask me about the project if you want. But one of my favorite illustrations that's simple to explain to people about math is when you put siding on a house, you put horizontal siding up like this, and you put pieces up. And this is really easy through here because they're all the same exact length. But what happens when you get here? Well, now they start getting shorter and shorter and shorter and shorter. Well, people that don't know math have to literally measure every single one of those. And what happens is there's 2 people standing up on a scaffolding, and they take a measurement, and then they turn and call it down to the person on the ground with the saw, and the person on the ground with the saw cuts them while the people on the scaffolding are standing there doing nothing. And then that person on the ground hands them up the board, and then while they're installing it, the person on the ground is doing nothing. Well, if you know math, you can actually calculate the lengths of all of those links. It's just proportions. But the question is, do you know math well enough to see that you could insert it there? If I ask those carpenters, do you need math? They'll say, well, as long as you know measurement, you're fine. And I would say, well, yeah, but it's gonna take you 5 o'clock to finish that, and I'm gonna be done at 1 o'clock, because I can cut the whole rack on the ground myself, climb up the ladder myself, and install all those with one person and not 3. Or better, 2 people are up there installing one, and I already know the next length, so I'm cutting the next one. So when they get it installed, they turn to me and I'm handing them the next one. That way we're always all working, and now we're done at 1 o'clock. So like, do you need math? Well, no, you can get it done without it. Yeah. But has it made me a lot of money in the construction world? But the problem is you got to be, well, like this good at it. That's the problem. You got to be good enough to insert it where it can belong. And it's not going to always be obvious that there's something that you can know that can save you a bunch of time. And so, ultimately what I'm hoping for all of you is that you learn to think deeply enough that if you're in some situation like this, even though that's not a calculus problem, that you would say, gosh, it seems like there should be some way to figure that out. I wonder if I could draw pictures and try to figure out if I could do that. That you at least would not be afraid to ask that question. That's what mathematicians do, or that's what people that aren't afraid of math do. And maybe the answer is, yeah, you can. Maybe the answer is, I bet there is a way. I can't seem to figure it out. I think I'll call my old calculus teacher that taught me derivatives and integrals back in 2021. Maybe he can help me. At least to, ask a question. All right. I'm going to shut up for today. And if you want to ask me anything about today or about the project, or if you want to talk amongst your group, exchange phone numbers or whatever, feel free. Some of you are hitting each other up about Discord. I love it. Thank you for posting that, Becky and Justin. Adrian weighed in. Sweet.